Module 6 in 3rd edition is one of those modules that really brings to light the differences between the 2nd edition and the 3rd edition, because in the 2nd edition, this is the time in your study when we would be talking about classifications of matter as mixtures or homogeneous substances. Homogeneous mixtures, heterogeneous mixtures, or substances, and distinguishing between pure substances and mixtures. We've already done that part, right? Okay, so I'm thinking back on, no, but this is the class we've already done that in. But that's how this module would normally, or started for years during the 2nd edition. Now we're in the 3rd edition. And we're going to just add to that conversation where your 3rd edition starts with the classification of changes that occur in matter. And there are basically two large categories of classifications of change in matter: physical change and chemical change. We may have spoken about this a little bit when we did mixtures and substances, because again, in my learning and my preparation, those two things came right back to back. But just to refresh our memory on this, the difference between a chemical change and a physical change. A physical change just means something physically has changed with the substance that you have, but it has not affected the individual atoms or the molecules. Nothing has chemically changed. That's maybe the way to contrast them. A physical change is different from a chemical change in that in a physical change, nothing actually occurs to change the atoms or molecules that make up the thing. It just looks different. A chemical change is a change where, because of a reaction, the actual structure of the atoms or molecules has altered. Something is different about them. We joke about getting on Miss Frizzle's school bus. If we went down to the molecular level and we saw a physical change, we may not recognize any change. At that close to the atoms and the molecules, nothing might appear to change when we go through a physical change. However, if we go through a chemical change, we would see the individual clumps of matter, whether atoms or molecules, rearranging themselves in different ways to become something else. In a physical change, all that really changes is the appearance. In a chemical change, you have the building blocks that make it up suddenly rearranging themselves to become something else. You'll still have all the pieces, but they will have rearranged themselves in some different way. One of the classic ways of understanding this is take a piece of paper. You have a blank piece of paper, Will? I could borrow? Tell you what, I know I'm not going to get through all my notes, so I'm going to sacrifice one of my notes. I don't think we're going to get to page 5 today. So, sorry, page 5, nothing personal. Okay? I've just produced a physical change. Okay? I haven't affected the atoms or molecules that make up the paper and the ink. Nothing has happened to them. This is where I was saying if we were in Frizzle's school bus and we were really close down at the molecular level, we might have been in the middle of this paper. Nothing's changed for us. Nothing's really changed. It looks different to you and I, and somehow it's funny, but it looks the same to you and I, right? It's Tuesdays. We always laugh on Tuesdays. Come on. Okay, so it looks the same to you and I, but I haven't really done anything to the paper. And though it would be very difficult, we could reconstruct this. We could take these pieces and, you know, when you've gone through the garbage to try to read that letter that somebody ripped up on you, go through and put it all together and tape it together. And if we were really wanted to, we could use microscopes and little fine tweezers and glue the individual fibers back together, and we'd still have the scars. You know, it might look like Frankenstein monster, but you'd be able to figure out what it was, right? You could read the content on the page. Now, that would be a physical change. If I took the paper now, and does anybody have a match? Okay, good. But you take these pieces of paper and burn them. Now, I'm adding energy and I'm changing the molecules that make up the substance by adding heat to it, and it burns. hopefully you come to understand that combustion is the chemistry word for burning, combustion is a chemical reaction. By adding heat, what's actually happening when you burn something, like let's say a log at a campfire, looking forward to camping this weekend, okay? So you add heat, that heat around the wood causes the wood to release gases. Those gases are flammable and they burn. The actual solid wood itself doesn't burn. It's the gas that the wood releases that burns. Okay? And so when you start with this big pile of logs and you finish with your s'mores or whatever and you go to bed that night, you come out the next morning and you see this little pile of ash. And if I were to go to you now, go ahead and glue them back together to make the logs. Like, I can't do that. Why? The ash itself is chemically different than the wood. I've actually not captured everything because as those logs were heating up and releasing gases, those gases were combusting, the chemicals that make up those gases were changing, and then they were escaping. I don't even have the same amount of matter that I had before. If I had known you were going to do this, Mr. Baker, I would have at least burned in a container that would capture all the gas. But you know what? Even at that, if I had all of the atoms that were originally there, they're not in the same form they were before. So I can't just glue them together. I can't put the solid together and inject the gas and have a log again. It's something fundamentally different. And because it's something fundamentally different, it has undergone a chemical change. It's not what I had when I started. Now, this is closely related to the idea of phase, which is actually the next section we're going to get into. But, you know, a classic elementary science project involves a solid. Okay? This is a solid. Baking soda. So you can imagine now, what am I going to do? Yep, going to add some vinegar. So what's it going to do? It's going to smell like the weekend before Easter up here for a moment because you're coloring eggs, right? Oh, Tyler's not here. I can't give him a drink. Okay, so I have this solid and I have this liquid. When I combine them together, what do you anticipate is going to happen? Bubbles. What are bubbles? Gas. Now, if I had a balloon over the top of this, what would we anticipate would be happening? The balloon would be filling because some of the elements that make up the liquid and some of the elements that make up the solid are combining and resulting in a gas. So if I said to you, I want you to separate out the liquid and the solid, even if you could do that, would you have what you started with? We've lost some things, some gases left. Okay? And the only way I could ever get back to what I started with, in this case, would be to reverse the reaction. You can reverse, or you can go back to the original case if you can do a counter reaction, if you can reverse the reaction. But it takes a chemical reaction to reverse a chemical reaction. But it's extremely, in some cases, extremely difficult to do. Physical changes are relatively easy to fix. Like, relatively easy is gluing that paper back together is relatively easy as compared to reversing some chemical reactions. But you've seen all three phases in here as well. You've seen a solid and a liquid react to produce a gas. And at the same moment, you had all three phases in here. All the bubbles, those represent gases. What you see, the liquid, and under the liquid there are some solids. And hopefully you agree that invisible to us, gas has been released into the room, carbon dioxide. Okay, so this is a chemical reaction that leaves me at the end with atoms and molecules which are fundamentally different than what I started with. If I were to take that same volume of salt and put it into water and stir it up, it would appear to disappear. There wouldn't be any bubbles, so we wouldn't get any gas phase, but it would appear to disappear. And I would ask you, do we have a physical or a chemical change for salt water, making salt water? Is it a physical or chemical change? Salt and water, making salt water. It's a physical change. It's not a chemical change. Why? Because ultimately, they don't react, right? Ultimately, at the molecular level, I still have H2O molecules and sodium and chlorine ions, but I haven't changed them into something different. The nature of sodium chloride, salt, the nature of an ionic compound like that is it will separate into ions when it's in water, but they're not going to react with the water to make something else. So when you drink it, like I drank my salt water the other day when we did the lab, I was drinking basically salt and water, which makes up salt water. It doesn't become something else. And I mentioned at that time, if I took sugar and I stirred it into the water, would it create a chemical or physical change? Just physical, right? Because the individual sugar molecules, in that case, the molecules don't break up. They're not ionic. They're not going to separate into cations and anions. They're going to stay together as whole sugar molecules because it's a covalent bond. But they're going to be individual individual molecules of sugar. When you have a scoop of sugar, you have a whole bunch of individual molecules of sugar all closely together. When you put them into water and they separate, they distance themselves from one another, but they don't react. So at the molecular level, you still have water molecules and sugar molecules. They haven't become something else. They haven't reacted to form another compound. Okay? So that's the fundamental difference between a physical change and a chemical change. A physical change does not affect the constituent atoms or molecules. A chemical change means you're making something else. And also, with regard to reversibility, a physical change is relatively easy to reverse. A chemical change requires another chemical reaction to potentially reverse. Okay? So just keeping those two distinctions in mind between a physical change and a chemical change. On your own, it says, classify the following as physical or chemical changes. This is on page 211, 6.1 on your own. Let's just think through these and answer these together to kind of reinforce this idea between, or the difference between a physical change and a chemical change. The first one there, classify the following as either physical or chemical. Steam condenses into water. Right, it's physical. When I say water, that's still an H2O molecule, right? But it's in a different phase. Going from steam to liquid is what we're talking about. But the structure of the molecule is still H2O. It doesn't change into something else. Gasoline burns in an automobile engine. Chemical. Does everybody see why that's chemical? You're burning the gas, the gasoline and the heat combining with oxygen, which is standard combustion, a carbon chain molecule. We'll get into this later, so don't worry about the detail of what I'm saying now. But this carbon chain molecule, you add oxygen and energy in the form of heat, which is the spark in the cylinder, guys, ladies. That spark is the heat that takes the gasoline and has a chemical reaction with the oxygen to produce gases which expand and shoot the piston down to drive the engine. And then the carbon dioxide and water come out the exhaust. You ever notice that when a car's running and you see the water droplets coming out the exhaust? That's not condensation from, some of it is, but not all of it is condensation from the environment. Some of it is the product of combustion. We had an incident in our home where our heater flooded. Now, how does a heater flood? Not from outside water, internally produced water. See, one of the products of combustion is water vapor. And if your drain gets plugged, which happened in our case, our drain tube got a piece of growth in it, some green stuff grew and eventually plugged up the drain. So the water from the combustion backed up and flooded the burner chamber. And all the water that was in there was a product of the reaction of burning the natural gas to heat the house. So it sounds counterintuitive. We've got a heat source that's flooding itself because it's making water. But that's one of the products. So here, burning gasoline, what you're doing when you burn it is you're actually making a chemical reaction, which is changing some of the phases and causing expansion, which we then harness that as energy to drive the car. But it takes a chemical reaction to do that. Third, a barber cuts your hair. It is a physical change because at that point, the barber is not making chemical reactions take place. He's just separating individual atoms, different strains, different molecules. He's separating them, but he's not changing them. He's just separating them. And not separating them into something else, separating them into the same thing, but at different places. See the difference? Okay. Milk sours. The souring of milk. The separation into layers, if you have non-homogenized milk, remember our discussion of homogeneous and heterogeneous mixtures? If you took raw milk before it went to the plant to be homogenized, you could take that milk, set it out, and it would separate into the levels of cream based upon the density, right? And so if it's separated out and you simply scraped off some cream to go make some butter and some ice cream and took the rest and decided to sell it as 2% milk, or took off even more to sell it as skim milk, which is where the phrase skim comes from, because they've skimmed off the fat as it separates out, okay? Which skim milk is basically muddy water, right? I mean, I don't get it. But anyway, the good stuff is what you take off. So that's a physical separation. But if you have milk that's soured, what's happening is there's a biological process taking place. Little bugs, I'll just say bugs, the little bio things are in there eating away, and they're producing waste. I mean, stuff in, stuff out, right? They're producing waste, and part of that process is a negative effect, the souring. There's a chemical process that's taking place. Things are being changed from one thing into another. And in that process, it's a chemical process. The molecules that made it up are no longer exactly the same as they were before. So souring of milk is actually a chemical process, not a physical. E says sugar is dissolved in water, and we've already discussed this. It's a physical change. Okay? Sugar dissolving in water is physical. Because at the molecular level, the sugar has not become something else, the water has not become something else. We've just taken a clump of sugar and a mass of water, and we've equally separated out the molecules so they're distributed evenly. But they have not fundamentally changed. Milk is poured on cereal. Just a physical change. Milk hasn't changed, cereal hasn't changed. They just happen to be in proximity to one another, forming a heterogeneous mixture. Right? Because your charms or your O's are float to the top, and in the bottom it's pure milk, on the top it's pure cereal, in the middle they're mixed a little bit, stuff like that. Okay. And an iron nail rusts. That's right, it is a chemical change. When iron rusts, it becomes iron oxide. It's oxidation, chemically speaking. It's a reaction of oxidation. So iron becomes iron oxide. The iron atoms are actually forming molecules with the air around them, pulling out the oxygen and forming iron oxide. So when iron, the nail, becomes iron oxide, we see that as rust. It's a chemical reaction that takes place on the outermost atoms of the nail as they react with the oxygen in the environment or the oxygen in water. That's why wet things tend to rust, because water brings oxygen in contact with the iron, and the iron wants to react with the oxygen to make iron oxide, which to you and me is rust. All right, so an iron nail rusting is a chemical reaction. And we're going to move right now, as the book does on page 211, right into this idea of phase changes. Now, I probably hit this hard before, but again, I want to hit it here again, because if I did it earlier, again, this teaching is a little bit out of order from what I'm used to. But this is significant. Hopefully, I've mentioned it before. If I haven't, this is your opportunity to hear it. If I did say it before and you didn't hear it, here's your second chance, okay? Every single element on the periodic table exists in all three phases. Everything exists in all three phases. What I'm saying is everything that we know that exists in solid phase, liquid phase, and gaseous phase. Okay? The fact that sometimes people will say, is something a metal or a nonmetal? Remember we had this discussion? This is probably when it came out in our class. A metal or nonmetal. And some people will say, well, of course, oxygen is not a metal. It's a gas. The logic there is wrong. Or some people might say, but sodium is a solid. Is it? What does it mean for something to be solid? What does it mean for something to be liquid? What does it mean for something to be gaseous? And I would submit to you that the individual sodium atoms, they may not know what they are, if they're solid, liquid, or gas. It's not up to the individual atom to decide. Phase is kind of like a community relationship, kind of like a group of people take on their own persona, okay? And the individual kind of loses themselves in the persona of the whole. And so think about each individual. Is he completely out? No, just checking. Don't pretend to be sleeping if you're not. Okay. Each individual atom isn't the determiner of whether it's solid, liquid, or gas. Each individual atom exists as an individual atom. Its phase is how it relates to those around it of its same type and what that relationship produces. So like yesterday when I was teaching Algebra 1 and we were going over absolute zero. We've had that conversation in here, right? You go to absolute zero, and apparently things that exist have zero volume. How do we understand something existing and taking up no space? All motion stops. So time stops because time only has meaning relative to motion. You know, all those kind of weird things start happening. Okay. With this whole idea of volumes going to zero is this relationship between volume and temperature. Hopefully you would agree that if I have a balloon, I don't have one here obviously, but if I had a balloon and we saw that it had a certain size, if I go ahead and I heat up the contents of that balloon, what would I anticipate to happen to the balloon? If the gas inside were heated, what would happen? Balloon, inside hot. Balloon expands, right? Think of a hot air balloon, one that you would ride in, okay? It's just there. They light the fire. They try to hold it so it doesn't burn the balloon until it gets started. Hot air goes into that balloon. The balloon goes up. And as the air is heated, it expands. And as it expands, its properties start to change because inside that balloon, the same volume of air, because of its temperature, has a lesser density than the air around it. And so whether you think of it as that balloon rising like a cork going to the top of the surface of the water, the balloon rises, or if you think of it as the other air around it that's more dense, shoving for space below it, the net effect is the balloon fills and then the balloon rises. Okay. If I take that same balloon when it's full and I were to stick it in some supersized cooler, what would happen to the balloon? What happens to the air inside the balloon? The heated air. It begins to cool, right? And as that air cools, the balloon is going to start to deflate. Maybe we should do this. Come up with 3 balloons. We'll take one, we'll put it over top of a heat source, maybe boil some water and kind of set the balloon on top of the beaker so it's not directly into the water. But as it heats up, the balloon would expand. Take another balloon, or maybe even the same balloon, run it over and stick it into a refrigerator, and then go get it at the end of class. And you'll see a balloon expand because of the heat, and then because of the cooling, which is the negative heating, have it retract. Okay. Kind of a little away from our phase change and more into density, but I want to go right now back to phase change, because the point there being that at the individual atom or molecular level, the individual atom or molecule isn't determining its phase, but everything can exist as a gas, a liquid, and solid. The reason why nitrogen, oxygen, they appear to us to be gases is because in the temperature pressure domain that we live, you know, where we as human beings will cease to function if we're under too much pressure or too little pressure, and will cease to exist if the temperature is too hot or too cold. We kind of have this little range where we kind of exist at. You know, if suddenly the temperature of the world plunged to negative 100 Celsius, a lot of us would die before we could react to that. If suddenly the atmosphere changed to 25 atmospheres instead of 1, we would all be laying on the ground going, I'm going to die, okay? Because we live in a bubble, a little range. And in that little range, certain elements have certain properties. In that range, we're used to seeing iron as a solid. The reason we can pound a nail into pieces of wood and have it be a solid nail is because it exists in that domain of pressure and temperature that we exist in. If we were suddenly to change it, if we're suddenly to incredibly increase the temperature, that iron would become a liquid and our deck would fall apart because the iron solid that we're using at this temperature and pressure would become a liquid at another temperature and pressure combination, and it would no longer be a solid, it would be a liquid. And who goes out and builds a deck and tries to pound in a liquid nail? It doesn't work. Oh, by the way, your hammerhead would be a liquid at the same time, and so you'd be shaking a stick at liquid trying to make it hold together as a deck. It's not working. So this idea that every element exists as a solid, a liquid, and a gas. It's not always one or the other. Matter of fact, as we go towards absolute zero, theoretically, everything becomes solid. So that at absolute zero, everything is simultaneously solid and takes up no volume. How do you understand? Yeah, no, boom, right? Okay, we're done. That's why we stay, deep space is 3 degrees Kelvin, and so that's as far as we go, because after that, it's kind of like whatever's beyond that domain, we're not sure. But something weird happens. We can say that. All right. So again, 3 phases, liquid, solid, and gas. So what is it that fundamentally determines if something is going to be a solid, a liquid, a gas? And that fundamental thing is the energy level. You'll see there on page 211, about even with the bottom of the green box, it says, the first thing to realize about phase changes is that they require only one thing, energy. It's the energy that's present in the sample that's going to determine whether it is a solid, a liquid, or a gas. Not the chemical makeup of the thing. Not the type of atoms, not the type of molecules, but the relationship between the atoms or the molecules. And that relationship is based upon the amount of energy in that sample. Okay? For example, you all are individual molecules or atoms in a sample, right? You're in first period chemistry. It's been cold outside. You've had a long night finishing your English papers. You come into first period chemistry, and the heat in the room, and the fatigue from last night, and the energy level in here is just, right? It's not happening. You're all acting like solids. You're just kind of here. But if something started to motivate you internally and get you going, like you suddenly, like William's over here sipping away at his drink, okay? They get a little bit something going. I've got my coffee over there, sipping at my coffee. Something gets me going, okay? You get a little more motion going, okay? You start to get a little more activity going. And that's what happens with atoms and molecules when we put heat, when we put energy into them. And the basic way we understand energy for molecules is heat. So think of energy and heat. It's a form of energy that we're heating something up. If we take something and we heat it up, we give it more energy, what starts to happen? A little bit more motion. I mean, we're no longer just faking sleeping, right? Matter of fact, we're all awake. You're all paying attention. You're all looking around. Then add even more energy. It's like, oh, we're about to leave for the holiday today. I'm really anticipating this. I'm really ready to go. So by the last period, in the first period, I can't get your attention. In the last period, I can't get your attention, but for different reasons. First period, you're sleeping. Last period, you're bouncing off the walls. In the first period, you're acting like a solid. 8th period, because it's club day today, 8th period, you're going to be like gas. Full of hot air. No, I mean, like a gas, right? You're going to be all over the place. It's going to take up more space to contain you. Why? Because you guys are going to be all active, like, hey, get out here, right? You're taking up more space. Now, I could pack you into one little corner because you're all just kind of like, whatever. I'm fine. Okay? That is the fundamental difference between solids, liquids, and gases. The energy that they have and that the energy that they have produces a relationship towards one another. If you're just going to all sit there and be like little lumps, it's going to look like yesterday's tornado drill. We pack you in side by side, bring you all together, and you don't move, right? Why aren't you moving? Movement takes up space. Movement requires energy. So you pack you in tight, and I would suggest to you that's what it means to be a solid. If we take water molecules and we pack them very tightly together, and they stay tightly together because they don't have a lot of extra energy, that they're going to come together and form a solid, and we're going to look at that and we're going to see ice. In our minds, the individual water molecules form ice when they come together. And a whole bunch of them together like that is an ice cube or chunk of ice. Okay? If we add heat to that ice cube, what happens? It melts. Yeah. It's hard question day. We add heat to ice, it melts. Okay. Now, as ice, its chemical formula is H2O. As water, liquid water, what's its chemical formula? H2O. Oh, a physical change. This is not a chemical change. Phase changes are physical changes, not chemical changes. So I've gone from a solid to a liquid. Now, I want to change its phase again. I want to take it back to a solid. What would I do? I take away heat, I cool it, and it would freeze again. Or, as a liquid, if I add heat energy to it, what's going to happen? Evaporate and become a gas. The gas has a lot more energy in it than a liquid does. And a liquid has a lot more energy in it than a solid does. Because the individual atoms change their relationship with their neighbors. And if you want to visualize it, as a solid, they sit like this. As a liquid, they kind of get their elbows out there. They need a little more room. Hey, back off. Don't sit so close. You know? And as a gas, they're pushing everybody away. The way I typically show this with my hands is that as a solid, a liquid, and as a gas. And it looks corny when I do this, I know. But it helps you remember a solid, a liquid, and a gas. It's about the energy and the relative motion of the molecules and atoms to one another. So let's think about it this way. As a solid, solids move. Here's the point in the book talking about the kinetic theory of matter. They even say in there, the page you're looking at and the ink on the page that you're looking at appears to be staying steady. It's actually moving. It's moving. Because the only stuff that doesn't move, well, put it this way, all matter moves. If you don't move, you don't matter. I mean, no, that's not what I mean. All matter moves, okay? So even though it's a solid, it appears to us like it's not moving, but it is moving. Why? It's not at absolute zero. It has energy. All matter has energy in it, and it receives and gives off energy. And so in my display of solids, when I do this, I don't just sit here and go solid. In order for you to remember this, I go solid, and I shake my fists back and forth. This is solid. Solid is not here, steady, nothing's moving. That's only theoretical at absolute zero. Anything above absolute zero means there is energy present. And if there's energy present, there's motion. And there's a motion here. Usually we refer to this kind of motion as a vibration. We say that solids vibrate. Okay? Solids vibrate. Now, why does it appear to us that this is not moving? The only thing that's shaking is my 52-year-old hands, right? But why is it that I can say that this book, this podium, they're all moving? Don't look like they're moving. They don't appear to be moving. I'll submit that they are moving. If they are moving, why isn't it moving? Why isn't it physically moving, like vibrating across the floor? It's like one of those little old-fashioned football games where you plug it in, the vibration table, and the little football players all over the place. Why isn't that happening? Because just like in our molecular geometries, where we had forces that were equal and opposite, that as we look at a solid like this, for every time there is an atom or molecule that's moving one way, there's a counter movement in the other way, and their motions offset to make no physical motion that we can detect. At the molecular and atomic level, they're moving, they're vibrating. But at the macro level, the big level that we see, all those minor movements offset one another to create no net motion. Now, if we were able to align the motion of all the molecules and all the atoms so that while they all vibrated left, they all vibrated left together, and they all vibrated right together, you could make an argument that this thing would be going back and forth. Okay? But because they're not aligned, they're not synchronized like that, they offset one another, and the net effect is no movement. Just like there are positive and negative charges on here, but they counteract each other, and the net is zero. Same thing with the motion. Motions left, right, up, and down, they're counteracted by opposite movements at the same exact moment, and the net effect is no motion. Okay? So at the atomic and molecular level, yes, there's vibration taking place. At the macro level, looking at the whole thing, it's not moving across the floor. It's not happening because they're offsetting. That's the solid. When we add additional energy, we move into liquid phase. Liquid phase. Now, there's still contact. This is why I keep my wrists together. Looks like I'm doing like Wing Chun sticky hands, right? So go watch Ip Man. You'll make sense. Okay, so this martial art form. Sorry, I was a full contact karate guy in college, so you're doing sticky hands practice. So you keep your wrists together, but the motion of liquids is this kind of a motion. The liquids never, the molecules and atoms that make up the liquid, never get that far apart from one another, but they're much more fluid. Oh, that's why we call them liquids, is they're fluids. Why? Their motion is fluid. There's a lot more freedom. They're not fixed in place with one another. And if I were to take this leftover from our reaction earlier and just concentrate on the liquid portion of this, if it were sitting still for a long time and it was not moving, and I were to say to you, the fluid in that beaker is moving. Do you believe me? Is it moving? Kinetic theory of matter says if solids are moving, then liquids are moving even more. Even though they don't appear to be moving, because they're in a confined space, there is motion that takes place. One of the experiments we've done in the past is we take 3 different temperatures of water and put a drop of food coloring in each one. Put a drop of food coloring in nearly frozen ice water, put a drop in room temperature water, and put a drop in water that was just recently boiling. Now, over a period of time, all 3 samples of water will come to be the same hue of the food coloring. Now, granted, the one that is hot will become fully colored quicker than the one that's at room temperature. And the one that's at room temperature will become fully hued quicker than the one that was nearly frozen. All 3 will change over time. The reason being is all 3 samples of fluid, of liquid, of water, all 3 of them, the molecules are all in motion, but at different speeds because they have different energies, because they have different levels of energy in them, because they just came off of different heat sources. So the hot water has a lot more motion, has a lot more energy. And because of that, it mixes with the food coloring much quicker. The room temperature at an intermediate rate, and the cold water at a slow rate. Matter of fact, when you drop the food coloring into the cold water, it just kind of sits there like a blob at the bottom. And sometimes it takes 24 hours for it to completely change over. And what happens there actually is it warms up the room temperature, and so it mixes in its last stages at the same rate that the room temperature sample did. So we've got different phases. We've got solids. You can see their approximation of what I'm about to draw on the top of page 212. You've got solids, liquid, and a gas. And if I told you that I had a sample of iron, what phase would it be in? How do you know? You say, Mr. Baker, I need more information. I'd say, okay, at standard temperature and pressure, oh, it's solid. How do you know? Because that element at standard temperature and pressure, the way we normally see it, is at that phase. So carbon dioxide, is it a solid, liquid, or a gas? Mr. Baker, I need more information. At a standard temperature and pressure, carbon dioxide is what? It's a gas. So is carbon dioxide always a gas? No. You know it is in its solid form too. Solid carbon dioxide. What's the common name that we give that? Dry ice. Dry ice is solid carbon dioxide. So if you said, I've never seen solid carbon dioxide, have you seen dry ice? Yes. You've seen solid carbon dioxide. What's the difference between liquid carbon dioxide and gaseous carbon dioxide? The amount of energy in the sample. The amount of energy in the solid is much less. Therefore, the atoms and molecules stay close together, so close together that they don't really move, they just vibrate. As they become a liquid, they have more freedom, more fluidity. And as they become a gas, then they're taking up much more volume. The same number of molecules take up less space, more space, and the greater amount of space because of the energy that they contain. So this is trying to show you you've got solid, liquids, and gases. In this place, we're going to, in this direction, we're going to add energy. And in this direction, we're going to lose energy. Adding energy, we know that as heating. We're going to call that for heating for our purposes. And losing energy would be cooling. So whatever I have, if I'm heating it or cooling it, I'm either adding energy or I'm taking energy away from it. As we go from a solid to a liquid, what process do we call that? If I have something that's solid and I convert it into a liquid by adding energy to it, it's a phase change, but that particular phase change we know as melting. I'm just going to write melt, but it's melting. To go from a solid to a liquid means we're adding heat energy to it, and the process of phase change from a solid to a liquid is known as melting. And then from liquid to gas, we add energy to it, and that process we know as evaporation. Sure, I'll go with that. So evaporation, or vaporization is the way they do it in the book, to vaporize it. So we melt it and we evaporate it. Those are all processes of adding energy to moving from one phase to the other. Going in the opposite direction. When we are taking something from a gas to a liquid, that is condensation. Not condescending, but condensation. Okay. So to condense something from a gas to a liquid, we take water vapor and we condense it, it begins to rain. Precipitation, rain, is condensing water vapor and making liquid water. And then the process of moving from a liquid to a solid, we know that as freezing. See, so we see all of those all the time. Now, there's also a process they don't have on here, but when we go from a gas, or excuse me, from a solid, and we can skip liquid and go straight to gas. It's called sublimation. I'm just going to write sublimation. To sublimate means to go directly from a solid to a gas. If you were to take a, don't do this, because it'll make Austin's grandfather very upset. But if you were to take a carbon dioxide fire extinguisher, okay? And yeah, where's Larry? Don't let him hear this, okay? He'd just be too tempting. But you get a carbon dioxide fire extinguisher and you use it. Solid comes out, right? And white, looking like almost like snow stuff, comes out. That's solid carbon dioxide. That's like dry ice. Now, for the most part, if you leave that solid carbon dioxide out, over time, it'll disappear. It'll disappear, and guess what? The carpet won't even be wet because it sublimates. It goes from a solid directly to a gas. It goes from being dry ice pellets, kind of foamy carbon dioxide, straight into carbon dioxide gas. You never have carbon dioxide liquid to saturate the carpet. So it ends up being dry at the end because it went from being a solid directly to being a gas. It sublimates. It's one of the weird phase changes that we don't talk a lot about, because the most common ones we're used to is solid, liquids, and gases. Now, yes? Plasma. Yeah, we're not going to get into plasma for this course. One thing I want you to think about, too, in terms of volumes. We're going to get into volumes and densities when we come back. Okay? Hi, welcome back. Okay, so into volumes. I want you to understand, don't put your heads down on your arms. It's like saying, you know, how far is too far and taking it right to the limit. Don't do that. All right, so looking at volumes, I want you to understand that we typically think of things with relationship to water, because water is the most common molecule that we know, right? Water is all over the place. It's ubiquitous. It's everywhere. Water. And we tend to understand things with regard to water. When I say I've got something that's frozen, you immediately probably think of ice cubes. And this frozen thing, and when it melts, you're like, oh, I can see ice cubes in my mind melting and becoming a liquid. Okay, cool. And then they become a gas. Well, they evaporate off. How is it that you have an ice cube on the counter that you forget about, and then the next day you come back and there's a little salt ring where everything that wasn't H2O was left on the counter as a solid because the H2O was all evaporated. And you know that it melted, made a puddle, and then evaporated off. You take the dishes out of the dishwasher. You got the little salt rings, right? Little spots. You know that there was liquid water on it, and it became a gas because it evaporated off and left behind the chemicals, the minerals. We think in terms, and that's fine in terms of the different phases, but when we get into this idea, it's startling, isn't it? We get back to this idea of volume, how much space does it take up when it's in these different phases? You need to remember that water and a few other substances, because of their hydrogen bonding, are anomalies. They're not the case for most things. For most things, when they're in the solid form, they're the most compact. For most things, the solid is where it's the densest. Okay, it's packed in the tightest. It's the smallest. So if I have a certain number of molecules or atoms of a substance in its solid form, that's the tightest and the smallest. And as we add energy, it takes up more and more space. So to go from a solid to a liquid to a gas is the way it typically works. And then to go from a gas to a liquid to a solid, where the same number take up less space at solid and most space at gas. But water is unique among a small number of compounds in that water actually has its smallest volume as a liquid. It has a greater volume as a solid, and it has the greatest volume as a gas. Which is why when you freeze something, and again, most of you don't use these anymore, but you freeze something like, you used to have to go fill up ice cube trays before used to go, refrigerator, give me ice. Before that time, you had to put trays in the freezer. You would never fill the tray all the way up because as it froze, it would expand and take up more space, right? So there's an expansion for water when it freezes. Most everything else, as it freezes, it gets smaller.